All right, so building on our Bronsted-Lowry definition of acids and bases, where we have a proton donor and a proton acceptor, we have what are called conjugate acid-base pairs. So here I have ammonia, and then I have ammonium. Ammonia gained a hydrogen ion to become ammonium. So ammonia is a base here. The ammonium ion is the conjugate acid because I have one extra hydrogen. Okay, now down here I have water and hydroxide. Okay, I lost a hydrogen when I went from water to hydroxide, so I donated a proton. Water acts as an acid here, and this hydroxide is a conjugate base. So every acid has a conjugate base. Every base has a conjugate acid. Okay, for our acid-base conjugate pairs, the conjugate base of the pair has one fewer hydrogen and one more negative charge than the acid does, and then the acid has one more hydrogen and one fewer negative charges. So here I have water and hydronium. So I've gained an extra acid and I've gained a positive charge. I've gained an extra proton. And here I have sulfuric acid and hydrogen sulfate as my conjugate base. So you have an acid and a conjugate base. You have a base and a conjugate acid. So here's some more ammonia and the conjugate base ammonium, water and the conjugate base hydroxide. Here I have hydrogen carbonate as my base and carbonic acid as my conjugate acid. And then I've got water as my acid and hydroxide as my conjugate base. Here's several more. So here I've got HF, I've got hydrofluoric acid and a fluoride ion. So that's my acid. And then the fluoride ion is my conjugate base. And then I've got water, and it gained a proton for hydronium. So I've got my base and the conjugate acid. So this is an acid, base. This is a conjugate base and a conjugate acid. Okay? The reactants are always the acid and base. The products are always the conjugates.